Hello there, data enthusiasts. I'm happy to be here today. My name is Olusesi Ibrahim Adebisi. I'm here today to present to you my project on IBM Data Science Capstone project, the advanced version. The topic of my project is credit card fraud detection and assessment system. As we all know, credit card fraud has been one of the main issues being faced by several financial institutions. Some of these financial institutions, they've had cases of having to cut out as much as 5% of their e-channel based activities through to fraudulent practices. Some to the even extent of 9% of their yearly revenue, which is quite big. And it gave room for concern for data enthusiasts because looking at the top 10 countries that that is affected by these fraudulent activities, top on the list of the top 10 is United Kingdom, followed by India and Brazil. And my beloved country, Nigeria, is 7th on the list, which is one of the reasons why I took it as my project, because I see this as a malice that needs to be addressed. The case study, for example, as the case study indicates, we have chosen to actually address this issue using both the supervised learning algorithm and also unsupervised learning algorithm. You see, this is more like an hybrid learning algorithm, whereby you have a case of you being able to learn from the past via the supervised learning, and you being able to detect new trends via unsupervised learning algorithm. The data set for this project was sourced from a previous project which was conducted in the year 2013, September to be precise. The data comprises of European card holders, the transaction of European card holders that occur in 2 days, which from where we have just 492 frauds out of the large chunk of observation of 284,807 transactions. As we can see, there is a huge imbalance between the target class, which is our fraud, and the total number of observation. So the imbalance is something that you need to work on in order for effective model deployment. In this project, what I have actually looked at, since this imbalance needs to be addressed, I've actually tried to employ oversampling minority class. What do I mean by oversampling the minority class? It's a process of getting the minority class, in this case, which happens to be fraud, to be very close to the same amount of non-fraud cases. So it is expected that in order for us to make this balance, you need the target class of fraud to the target class of non-fraud transactions to be close to the same thing. So they should actually be close to 50-50, as shown with as shown with as shown here with the batch. You can see after the oversampling, the data of the target class, which happens to be the fraud, is close to what we now have for the non-fraud cases. The way in which this is implemented will be explained later. The data quality assessment for this project had to do with looking at the null data cases. Do we have null data or don't we have null data in this data set? Because the presence of null data will bring about bias in the performance of the data set. So this data set was actually looked through and found not to contain any null data. This is possible because the data was sourced from a previous project for where principal component analysis has already been implemented. And as we all know, principal component analysis can actually not be done without you removing null data. So in this particular data set, we do not have null data. But we need to really find to see whether we have duplicates in this data set. Investigation from this data set indicate that we do have some duplicates in the data set, and these duplicates will actually work on, as shown. We have over 1,000 duplicate transactions. The data exploration. Let us go through what we have in the data set. In this data set, we have 31 features, and we have 284,807 observations. The number of features in this seems large, but as we all know in data science, in order for you to really get performance, you need to explore all possible avenues. So let us see, do we have correlation in between these columns? Do we have a case where one is extremely large and we need to work on? We'll look at that now. What format do we have in this data set? And as shown, we have from column V1 to column V28, we have float 64 data type. We have time, which is integer 64 data type, and also we have amount, which is also float 64, and the class, which is integer 64. This will give us an evidence to really look at, because we need to really look at this data and see, in order for you to really understand how their relationships are, their data type also need to be put into consideration. And as you can see, most of all these columns are of data type float 64. So the data type is ready for exploration. The first port of call in our data visualization and also exploration is using correlation matrix. Correlation matrix will give us the interrelationship between the target columns. And in this project, the target columns are found to be from V1 to V28, and also amount and class. So, according to the correlation matrix seen on the, you can see that there is correlation all through the data set. So if we don't really have correlation, we will have some scanty blank white spaces. But you can see we have patches almost all through the data set. So which gives us an indication that there is correlation between the highlighted columns. Another way is for us to look at the spread, the data spread. Although time and amount cannot be used because they are more like continuous data type, but leveraging on the columns V1 to V28, we can see that the box plot is showing a spread around plus 20 and minus 20, which is telling us that the data spread within these columns are actually ranging around the same area. If you can see very well, because this particular data set is between the ranges of 20 and minus 20. So this data is evenly spread. And we can really see some outliers. These outliers is one of those things that we need to really find a way to learn about in this data set, because in most cases fraud are close to or anomaly data set. So the abnormal behavior will actually come in form of some outliers in some situation. Let us look at the multidimensional relationship between these data. As you can see on the observation, for each of the observations from the data set, there seems to be a tight relationship between the columns. As you can see, almost all the columns have relationship in between them. So this is an evidence of how close this data set is in relation to the fraud data and non-fraud data. Most of what we are seeing here represents the normal data set, that is the non-fraud data spread. This is also another one that is gotten from peer group plot. As we can see, trying to really look at the probability of having fraud and non-having fraud, you can see that in most cases the fraud patches are not compared to the non-fraud patches. This is another way of really getting to know the imbalance between the target class of fraud and non-fraud. Now let's go to the fraud rate. Let us see what is the rate at which you have fraud compared to the non-fraud in the data set. Using scatter plot, we can see that the class of 1, which happens to be our target, the class of fraud, is quite imbalanced compared to those non-fraud observations. So this gives us that the rate of fraud is significantly rare compared to the non-fraud observations. Within our features, we need to do some feature engineering. An example is what I made mention earlier. We have the time column, we have the V1 to 28 column, we have the amount column, and also we have the class column. What we discover is the fact that if we try to actually put the value of these columns in relation to themselves together, there will be a bias towards those observations or entries coming from the columns with large values. So in order to really ensure we don't experience this, we are actually using the min-max scaler in this project. What the min-max scaler does is to look at the highest and the minimum within the data set and scale it between 0 and 1. So most of the columns that we have were actually min-max scaled, and after the min-max scaling, if you check through the data, you find out that the data is between the minimum and the maximum, and that is for the continuous one, and scale between 0 and 1. So with the scaling between 0 and 1, we are going to ensure we are not going to have a bias that can be introduced due to large data from some columns. So this is part of the feature engineering that was done on the data set. Now, another part of feature engineering carried out in this project is the oversampling the minority class. You can see what we have here is a sampled plot. The previous one that we had was showing the real one compared to the oversampled plot. The oversampled plot is still going to tell us how the fraud can actually still be spread out to cover close to 50%, so that at the end of the day the imbalance will be removed. That is the purpose of the oversampling the minority class. Let us compare between the data that we didn't apply oversampling minority to compared to the original data. And from what we have, you can see that the plot is still very close to the same, except for the fact that the sampled data is now having more of the fraud cases and is also in the neighborhood of the original fraud cases. So from the plot, you can see the plots are still very much similar, but we now have more of oversampled, or more of fraud cases introduced by oversampling the minority class. Now let us go to the performance, the model performance used in this project. In this project, one of the main performance indicator that was used in this project is receiver operating characteristics, ROC curve. Receiver operating characteristics is far better than accuracy, because in a fraud case like this, the data imbalance is of essence, because the data imbalance is huge, and since the data imbalance is huge, accuracy cannot be relied upon to give us performance. Accuracy is highly affected by imbalanced data set. And as you can see, what receiver operating characteristics about is the tendency of you having the true positive rate and the false positive rate. So as you can see, this is the optimal threshold part of the ROC. So unlike the direct part of accuracy, which is of the straight line. So you can see that when the ROC is giving us a threshold, the accuracy is giving us something different. An example is what we have here. The threshold accuracy here is saying 0.92, and you have here the threshold accuracy is telling us 0.8 for the same data set. And that is the more reason why in an imbalanced data set, ROC can actually be of essence. But before ROC, we have some other ones that we need to also look at. F1 score is also used. F1 score is used when false negative and false positive are crucial. And in this fraud case, we know that you will not want a case that you say a particular transaction is not fraud and is later found to be fraud. And also you will not want a case where you call a particular transaction as fraud and is later found not to be fraud. So F1 helps us to address this, so that at the end of the day our model will give optimum performance. And as you can see, the actual class will tell you, okay, you can see here the true positive, the true negative. Those are our targets. But the false positive and the false negative, those are areas that we don't really want to have our model to predict. So in most cases, you see precision and recall are also of essence. So we now have three metrics that we'll be targeting for this project. One is ROC, receiver operating characteristics. The other one is the F1 score, F1 measure. And the other one is precision and recall. So let us go to our model, and you can see before oversampling the minority, look at what we have for a model. You can see the ROC giving us 97%. You can see the precision. The precision is telling us for the fraud cases, the non-fraud cases, you have it, your precision as 100%, recall as 100%, F1 as 100%. That is for the non-fraud, because the data is tending towards that direction. Now let's look at what we have for the fraud target. You can see precision is telling us 100%. You can see precision telling us 100% here, and recall is telling us 0.79, and our F1 score is telling us 88%. This is an indication of the issue with imbalanced data. So let's see what we get after applying oversampling the minority. After applying oversampling the minority, we can see that our model has now gone to a perfect result. You can see our ROC is 100%, our precision 100%, recall 100%, F1 100%. In fact, even the fraud target in this case. In this particular test, the test data is around 85,000 of the 284K data set. And you can see we have 147 frauds. 147 frauds. And out of this 147 fraud, so out of the 147, you can see that we have all the data, even the conviction matrix is indicating here. You can see what the conviction matrix is indicating here. The conviction matrix is telling us so as seen from this data, you can see that oversampling has helped us to arrive as a very good model performance. we are looking at the conversion matrix here, we can see that our target of getting all the fraud was achieved. As we can see from what the support is showing here, the support is telling us that we have 85,296 non-fraud cases against 147 fraud cases. And the conversion matrix is telling us that we got everything right. We got our true positive right, and we got our true negative right. So we got our stuff very close to perfection. This has given us a perfect result, and we don't always get this kind of result every day in data science, but this is when you actually have a good, you get a good process of preparing your data and using the appropriate technique, you are going to get something like this. Okay, on some situation, fraud repository cannot continue to rely on previous experiences. There will always be a time where new trend in fraudulent activities will start coming up, and that is when we can actually bring in the effect of unsupervised deep learning to help us to filter out all those new characteristics of the new fraud trends. And that is what we are actually using in this project, whereby we employ the use of self-organizing map for identification of new fraud trend. Self-organizing map uses several artificial neural networks to arrive at picking new trend within data set, picking new cluster within data set. You will be able to see the new trend and will be able to tell us that these are the new trend, and from there we will be able to really incorporate this new trend into as our machine learning repository for supervised learning. And according to the performance of this particular self-organizing map, at the initial trend of 2 epochs and having a batch size as stated, we are able to achieve very close to 80% performance for these. This was actually due to the fact that we segmented the data that we use for this self-organizing map to 10,000 observations. From that 10,000 observations, we will notice that the number of fraud reported in that trend happens to be just around 20 something or 31 fraud cases. So this is a way with which you can actually pick the new trend, and once the new trend is picked, you will be fed into the supervised learning algorithm. Let us go through the definition, the performance of the use models. We started by actually using logistic regression model, whereby you see it is more of how to really get this boundary to segment where this one of which is fraud and the not fraud where they belong to. And what performance we got from using logistic regression happens to be also close to perfection. And you can see from the classification report, we got the precision for no fraud and fraud cases right. We got 100% for recall also for non-fraud cases, but we got 99% for fraud cases. And as you can see, the F1 score is also giving us 100% for the non-fraud cases and the fraud cases. So as you can see from the support, we had 84,289 for the logistic linear regression, and we have 127 for the fraud cases. And you can see from the conviction matrix here that we just missed out one of the target fraud cases. So also we use random forest model, and the performance of the random forest model gave us close to what we have here, in which we now have 84,989, and we pick all the 129 fraud cases. The reason why we are having 129 here compared to when we are having 147 has to do with the fact that the first data contains some duplicates and this one does not contain duplicates. That's why the number reduced from 147 to 129. So in this particular case too, we got from our classification report, we got the precision, we got the recall, we got the F1, and we got all the fraud also, which when we have precision here, precision, recall, and F1 right for the fraud cases. So this is a perfect one also. So the random forest from here seems to give us improved performance compared to logistic regression. So in conclusion, we can see that the logistic regression and random forest were found to be effective learning with large data. The 100% ROC precision recall and F1 score from both logistic regression and rainforest from the large data set, with exception of recall at 99% for logistic regression, gave the learning efficiency of having large data. The self-organizing map also was found to be effective for identifying new trends which can be fed into highly effective supervised learning model for improved performance. With this, I believe I've been able to do justice to this hybrid system of combining supervised learning model with non-supervised learning model to give us a close to perfect fraud detection system. Thank you for your time. I wish you best of luck. God bless you. Bye.